Bismillah ar-Rahman ar-Rahim. So this is a help session. I asked the way this generally conducted is they said it should be just quick revision. As you know, we don't have final exams that are shared with the students for some reason or the other. But what I can do here, I will stress on chapter 16 and chapter 17. I believe that these two chapters were recently covered, and sometimes students will feel that because maybe we used IBL, whatever, some students were not adopted to this new methodology. Anyways, I will go over chapter 16 mainly because multiple students called me from my section and their questions were towards chapter 16. I don't know if you agree with me or you have another suggestion. Okay, Shabab, so shall we go over chapter 16? All right. So let me now start with electrophilic, aromatic, substitution reactions. Now for the electrophilic aromatic substitution reactions, in general, you have benzene ring, and it's better if this benzene ring is, of course, activated. We will come later to this part. And you need here an electrophile, and this will result in formation of electrophile. Now, this electrophile could be nitro group, NO2 plus, could be Cl plus, could be CH3 plus, could be C double bond or CH3 plus. Now, of course, each one has its own mechanism, but I will try to merge more than one thing at the same time. The critical thing is that this reaction is generally faster when you have electron donating group. So there is a list of activators and deactivators. If you remember, let me just give you this is in the IBL. I think it's around like page 346. That tells you that the electron donating group here is considered as activator. So when you have a benzene ring that has nitro group versus when you have benzene ring that has cyano group, nitro group is considered the strongest electron withdrawing group. So this means it's called deactivator. Now you have, after this cyano group, you have carboxylic acid like CO2H. Then you have aldehyde, ketone, and then you have halide like X, and then you have R group, where R group is CH3, ethyl, methyl, any alkyl moiety, and then you have here the OR, and then you have the OH, and then you have an H2. I didn't list all of them, but this is to tell you that the speed of the reaction will go in this direction. So these here are called activators. So these are electron. These are electron donating groups, and the ones on the right side, on the left side, sorry, are electron withdrawing group. It is better to have electron donating group, okay? And the one that comes here is the benzene ring, which doesn't have electron donating or electron withdrawing. Now, it is better to have this as number 1, then this one among this list is number 2, then this is number 3, and as you see, nitro group will be the worst. So this means if I have two reactions, I have here, for example, nitro, and I have OCH3. Which one of these two will go a faster? For example, C double bond O, Cl with aluminum chloride, which is a Friedel-Crafts acylation reaction. In this case, the one below will be faster because this is electron donating group. So if I have two phenyl rings, this is one and this is another phenyl ring, where this phenyl ring has, for example, OH, and this phenyl ring has nitro. Now, which phenyl ring of these two will react when you do, for example, nitration? HNO3, H2SO4. Which one will react? The one that will react is the ring that is more activated. Which ring is more activated? We have to look at now. Nitro hydroxy. Nitro is among the electron withdrawing groups. This is electron withdrawing group, and this one is electron donating group. In this case, we know that the right side ring is the one that will react. So this ring will react regardless now if this is ortho para director or meta director. Of course, يا شباب, I cannot see any comment if somebody is commenting. Please just stop me and ask me if you have a question. Okay. Now, this is benzene ring that has NH2. Now, if we draw resonance forms, we know that this lone pair gives electrons in this direction, and then it forms this. This is double bond, NH2 and positive charge, and here you have negative, double bond, double bond. Another resonance form will be that this comes here, this moves in this direction, and now we have this double bond, double bond, double bond, NH2 lone pair. And then if you continue, there's another resonance form that is here, and here we have positive charge, of course. This is NH2 positive and double bond, negative charge. Now, from what we draw here, where are the activated sites? The sites that can act as nucleophiles, the ones that can attack the electrophile. This is the definition of electrophilic aromatic substitution reaction. We can see that the best will be this place and this place, plus of course this place, because we can see that the negative charge is allocated in these positions. So since we have the negative charge now allocated in these positions indicated by red, we say that activator, which is the electron donating group, is ortho para director. Electron withdrawing group is meta director, of course, for the same reason. I'll not spend a lot of time on this because it should be now a default for you that electron donating group is ortho para, electron withdrawing group is a meta director. So everything here is related to the resonance forms. That is if you have clear resonance forms like the case of NH2. But now for the case of CH3, if you have benzene ring that has CH3, then we know that the benzene ring will attack the NO2 plus, for example, or the Cl plus, or the CH3 plus, or the acylanium ion. And if we have the chance to go for ortho or meta or para, let's just put the ortho, meta, para. Now, if we say ortho, this means this double bond is the one that will attack, and that will give you the ortho. This is CH3, and this is double bond, and now we have the nitro here and the positive charge here, and this is the double bond. Now, if you draw the resonance forms, you can continue, you draw all the resonance forms, but now this resonance form will be more stable than the other resonance forms that will come from the meta. Because if you go meta, then this double bond, second one, is the one that will attack. And here we have nitro, and we have positive charge here. Now, drawing the other resonance forms will put the positive charge. This is CH3, this is positive, and this is double bond, and this is nitro. And another resonance form, this will come here. And now we have the positive charge here. So apparently, you can see that this is secondary, this is secondary, this is secondary. But now in the first resonance form here, we have a tertiary case. So this tertiary is a special resonance form. It has added stability. This can come here, and now we have double bond, we have positive charge, double bond, and nitro. You continue, this is going to form another secondary form. But this one is special, so we say that this is ortho para, because the para will result also in formation of these other resonance form. Of course, this is if you want to deeply understand why the activator is ortho para and the deactivator is meta. So this is the first thing that we have to figure out. And now the second thing is the sequence of events. Which one should be done first, which one should be done second? Okay, so now in some cases you have to do installment. For example, for alkyl group, we know that the alkyl group has a problem. So let us now look at this. This is Cl, and in presence of aluminum chloride. Now, what is the product for this reaction? This reaction suffers from more than one issue. The first issue, since we are going to form a carbocation, the carbocation can get rearranged. Rearranged, this means we will form this instead of just connecting the carbon that has the chlorine. So a rearrangement will take place because we are forming carbocation. Second issue, the reaction is not going to stop at the first alkylation. The reason you are forming now, when you form this product, which one is more reactive towards Friedel-Crafts alkylation? The product is more reactive than the reactant itself. So this means once this one is formed, it's not going to stop. It will continue to form the other substituent, which is the para. Ortho cannot be formed in this case because of steric hindrance, but it will continue and it will form this. So it's not possible that I decide to do this reaction and say that, okay, when I treat this with aluminum chloride, I will obtain this as a product. This is not going to work. The product will be this. You will form the para substituted and some of the ortho product. So the best way, if you are interested in this product, what do? You first take this and you treat it with C double bond O Cl aluminum chloride, and this will result in formation of C double bond O CH3. Now this one is electron withdrawing group. It will act as a deactivator. it will not go for further electrophilic aromatic substitution reaction. So now you stop the reaction here, and now you can add H2 palladium. There is another reaction that was covered, which will result in reduction of the ketone that is in the benzylic position, and it will result in formation of the ethyl ketone. Okay, so if you are interested in producing this, then you will not do direct Friedel-Crafts alkylation. You will do Friedel-Crafts acylation followed by the reduction. Friedel-Crafts alkylation suffers from the problem of rearrangement first, which is not a possibility in this case. You will not worry about rearrangement, but it also suffers from the هذه problems associated with Friedel-Crafts alkylation reaction. The problems associated with this: first, rearrangement. Second, it will go second, and sometimes third, alkylation. So you cannot control the reaction to stop at single alkylation. This is why the way you overcome this by doing Friedel-Crafts acylation followed by reduction reaction. So first thing to do here is to classify whether a certain group is electron withdrawing or electron donating, and then decide the sequence where you want to do the events. So now, when you have nitro group, you have benzene ring, and you do nitration, HNO3, H2SO4, then you know that the product will be a single nitro group that's installed. Now, if you want to do the second nitration reaction, you have to add HNO3, H2SO4, but you have to know now that the reaction will become slower. This reaction will be slower. Why? Because nitro is electron withdrawing group. It's a deactivator. So adding more deactivators to the ring will make the next reaction slower and slower, unlike Friedel-Crafts alkylation reaction. So I think this point should be clear, and the disadvantages of Friedel-Crafts acylation reaction should be again clear. Okay, so now when we have more than one reaction or more than one step to do, then if you have benzene ring and you want to go from this benzene ring to so let us say that you have here CH3 group, and you have here nitro group, and you are planning to do nitration reaction, HNO3, H2SO4. Then we look at the two groups that are available, CH3 and NO2. Now, we know that CH3 is ortho para director, and we know that nitro group is meta director. So this means nitro will push the reaction to go in this direction. Which one will decide? The one that will decide is the activator. And if you have two activators, then the stronger activator will decide. That's first rule. Second, you do not put a substituent between two substituents. Yani this side, I will not look at it. Okay? Because here we have steric factor that will say that I don't want to be between two groups. So this means the reaction will go in this position and in this position, which are ortho and para. Of course, this is a problem that is associated with the electrophilic aromatic substitution reactions, that sometimes you cannot get a single product. You will get more than one product. So the product for this reaction will be CH3 here, nitro, and nitro plus CH3 here, nitro here, and nitro here. So these are the two expected products. The one in the middle we will not get. So now, sometimes you have a reaction like this. You have a CH3 here, and you have, yes.
Which one is the stable one?
You mean which one is the major?
Yeah.
Both are major, because when we have a ratio between two that is 30 to 70 or 40 to 60, we say that both of them are major.
Okay.
Okay, so ortho and para will form in the case of activators. Now, if we talk about meta, which is the deactivator, you will get one product as 95%. The remaining will be 2%, 2%. Then you can say the 95% is major product. Okay, now for this example, when you have, I will comment on in another example on your question, because I think it's important to know this information. Now, if we want to do the reaction here, now CH3 is ortho, and of course left side it will be the same, right? So whether we put it here or here, it's identical. Now nitro is also meta, so this means nitro will also add here. So this is a question that will be an easy one, and if I go to the lab, I will be happy, because I will not, find any minor products in this case, because both agree that the coming group should be here. Now, if it comes in the left side, it will be identical. Now, if we look at a case like CH3, where you want to do nitration, HNO3, H2SO4. Now, we have to know two things: that the reaction can go ortho, here and here, or para. So it could be para, it could be ortho, but ortho will, you have two hydrogens. Yani if we work now statistics versus chemistry. Now, statistics says that two hydrogens should form ortho product. So you expect that the ortho product should be high. However, the para has advantage in chemistry. These are the two products. Let's just put them here. This is CH3 and this is NO2 plus. This is CH3 and this is NO2. Now, para product has advantage that it is coming, that it's formed as a thermodynamically more stable product. Why? Because we do not have any steric hindrance. Putting the nitro group and CH3 group in position 1, 2, you are causing some steric hindrance. However, this product here is coming from replacing two hydrogens instead of one hydrogen in the case of the para. So each product has an advantage, and you end up having them as similar ratio. So you expect that para should be more, but indeed ortho has the advantage of having two hydrogens that delivers the same product. So you can see that this product is coming from replacement of two hydrogens. So the possibility to see this or this in the solution is higher. However, para is giving a product that doesn't suffer from any steric hindrance. So these are the main things in chapter 16. Chapter 16, you have to classify the group as electron donating, electron withdrawing. You have to know which group is stronger electron donor or a stronger electron withdrawing group. So in this case, once you do this classification, you will know the coming group should go ortho, para, or meta direction. Okay, so this is the first thing. Again, second thing, you have to, of course, know the reactions. There is a summary at the end that tells you what are these reactions that will generate nitro. For example, when you see HNO3, H2SO4, you are adding nitro. And these two are used to generate NO2 positive. When you see RCl, aluminum chloride, this is Friedel-Crafts alkylation. This is to add R plus. When you see RC double bond O, Cl aluminum chloride, this is to add RC double bond O, Cl. Now there is no direct reaction for hydroxylation. Okay, and for amine formation, this generally coming from reduction. Yes?
Without Cl, yes?
There is, sorry, yeah. Okay, so this one is positive charge here. So finally, the product here is going to be a nitro group. The product here is going to be an R group, and the product here will be C double bond O R. Now, of course, you know, you will find some small modification from what you have in your hands. Some students, they have some slides from the previous semesters. Some students, they have some probably questions from here, from there. This semester we used a new strategy, which is the IBL, and whatever is available in your hands, this is the one that you are responsible for. Okay, so yes, other material might help you, but again, we skip some of the material that's available in the book, and this is not to distract you. This is to make you focus only on one source of information, which is the IBL. So this is regarding chapter 16. Clear يا شباب? Okay. Now, if we look at the material that you have in the final exam, you have chapters 11, you have no 12, 13, 14, we have chapter 15, we have chapter 16, we have chapter 17, we have chapter 18. Of course, these are chapters that you never been tested before, and you know that 50% of the exam will be in these chapters. Now, the trick to study, these chapters are connected. So if you look at chapter 17, chapter 11, a lot of similarity between chapter 18 and chapter 17. If you 11 and chapter 17. So this chapter talks about SN1, SN2, E1, E2. And when you go to chapter 17, again, you talk about alcohols. But when you talk about alcohols, you definitely touch on SN2, SN1, E1, E2. So nobody should study chapter 17 before studying chapter 11. Now chapter 18. Chapter 18 is related to chapter 8, which was covered in the second major. Chapter 8 has to do with reactions of alkenes. Okay, so reaction of alkenes are revisited in chapter 18. So you study chapter 8, you review it, then you go to chapter 18. Chapter 16, this is the chapter that I just reviewed. Chapter 15, you need to be able to classify any compound as aromatic, anti-aromatic, or non-aromatic. And just here, quickly to review, this is, if we look at this compound where we have negative charge and double bond, this compound where we have positive charge, okay, and this one where we have double bond and double bond, and this is benzene. Now if we consider the number of electrons, these systems first are planar, so we have to look at the system if it's planar, conjugated, and then the rule of 4n plus 2, where n equals 0, 1, 2, 3. This is 4n plus 2. So here we have 2, here we have 6, here we have 10. So if we have 2 or 6 or 10 electrons, we call the system aromatic. So quickly, these systems, this is 6 electron, this is 4 electron, this is 2 electron, and this is 4 electron. And now we can simply say that this one and this one are aromatic, and this are anti-aromatic. So they are planar but do not follow the 4n plus 2, which is Haeckel rule. Now how about if we have 5-membered ring that has a double bond and double bond with no positive or negative charge? This system, of course, is not conjugated. So we can say that this system is non-aromatic, not anti, none. So this one is called anti, this one is called anti, and this is none. Now if we move to this one, when we remove electrons, when we remove a proton and form this carbanion, this system now is 6 electron conjugated, planar, and this is aromatic system. If you have the positive charge, then this system is anti-aromatic. Okay, so the chapter 15 is a quick chapter and it's about classification. Now you know some of the things here that are commonly encountered in this chapter, that when you see nitrogen, lone pair, and not this one, let me just, and 5-membered ring. We have lone pair and we have lone pair. Now, which one is more basic? The left side or the right side? The way we should think about this is the following. Both systems are aromatic, but this lone pair here is needed in order to make this system 6 electrons, because this system is 6 electrons without the lone pair. So this is outside aromaticity, so this is outside the aromatic system, and this is within the aromatic system. The hybridization here for this one or this one is filling an orbital of p orbital, okay, and this lone pair is sp2, okay, and this one is filling the p orbital because this lone pair is included in the aromatic system, and this makes this system more, or this pyridine more basic than this one, because the lone pair of this one is involved in aromaticity. So when you say a compound is more basic than the other compound, this means the compound is included, or the compound is able to donate the electrons. It has a lone pair or a negative charge that can attack something else. So we see here the left side compound, which is pyridine, is more basic than the compound in the right side. This is related to the same topic. And if we compare now the pKa for this system, so here we have hydrogens, and here we have a benzene ring, and we have hydrogen here, and here we have a 3-membered ring, and we have also hydrogen. Then if I ask you which one is the most acidic hydrogen, the one that can be easily removed. Now if we compare these three together, I have to look at the conjugate base, the double bond here, and form negative charge. Here I will form negative charge, and here I will form benzene ring with negative charge. Now which one is the most stable carbanion from the three that I just draw? You have to immediately look at them, classify them. Which one is aromatic system, especially when you compare this and this. The one here is aromatic. Of course, you cannot deal with this compound because this compound is aromatic itself. Now, removal of this hydrogen, it's highly unstable. Now, this compound forms 4 electrons. This is anti-aromatic. So you think that removal of this proton will be easier, or removal of this proton will be easier? Of course, removal of this proton will be easier because you are forming an aromatic compound. So this means you will say that this one has a lower pKa. So this one has the lowest pKa. Lowest pKa يعني the most acidic proton. It's easy to form something that is carbanion. So all these ideas are for chapter 15. Chapter 11 is related to SN1, SN2, E1, E2. This is a lengthy chapter, but the material is easy to understand, but still you need to have 1-page summary where you can really classify, is this reaction SN1 or SN2? Quick overview here that the SN1 reaction goes faster with tertiary than secondary than primary. Okay? And the SN2 reaction goes faster with primary, secondary, then tertiary. Of course, the methyl will be faster, and generally the SN2 leads to stereoinversion, and SN1 leads to the formation of carbocation, and the carbocation will again suffer from the rearrangement, and it will lose the stereochemistry. So you have to be able to classify the SN1, SN2, E1, E2. Now, SN2, you need a strong nucleophile. E2, E1. E2, you need a strong base. And generally, the strong base, this is RO minus or OH minus. These are examples of strong bases. Strong nucleophile, I minus, cyanide. So these are keywords for SN1, SN2, E1, E2. Now, when do you think E1 will happen? E1 will happen whenever you have SN1. So E1 always competes with SN1. So you have to be able to classify SN2 first, then E2. So SN2, E2, and then the remaining will be SN1 in competition with E1. Okay, so this is chapter 11. Everyone should have a piece of paper that summarizes all the classifications of SN1, SN2, E1, E2 in 1 page, so that will enable you to connect the dots. Of course, you still have tonight and tomorrow you can play with these things. Now regarding chapter 17, chapter 17 mainly deals with alcohols. Of course, I will not describe everything, but let me tell you that the sequence to study is to go chapter 8, and after chapter 8 you study chapter 11, and after chapter 11 you study chapter 17. Okay, and after 17 you go for 18. Of course 18 is related to 8, 17 depends on 11, and parts of 17 depends on, you know, chapter 8. يعني the reactions of chapter 17. Finally, when you are preparing alcohol, you should know that when you have double bond CH3, you are adding BH3 followed by hydrogen peroxide, OH minus. Then here what you are doing, you are adding the CH3 and you are adding here, sorry, you are adding the OH in opposite stereochemistry, trans to the CH3, and in anti-Markovnikov fashion. If you don't know this from chapter 8, you will not be able to utilize it in chapter 17. So again, chapter 3, 4, 5, each one of them is talking about a topic that is different from the other topic. They are not really dependent on each other. Then you have chapter 6, a little bit different. Chapter 7, a bit different. Now starting from chapter 8, there is connection. If you do not know how to deal with chapter 8, chapter 17 assumes that you know chapter 8. So if you want to review the previous chapters 7 and before, you review them anytime. You can review before, after you study, but the sequence of studying these chapters should be 8, 11, 17, 18. Okay, now chapter 15 and 16, different story. They do not belong to this sequence. Okay, so chapter 8 first, chapter 11 second, chapter 17, then chapter 18. This is if you want to be able to connect the dots properly. The other reaction here that will give you Markovnikov addition is this reaction. HGO acetyl taken 2 and you add water. This is first, second, sodium borohydride. And now this will result in addition of OH group, Markovnikov fashion. So this is anti-Markovnikov, and this one is Markovnikov. Now, if you just replace this OH or this water, if you replace it with CH3OH, then what's the product? The product is OCH3. Now, this is a reaction covered in chapter 18, because what you made here is an ether, and what you made here is an alcohol. So this was a method to prepare ethers in chapter 18, and this is a method to prepare alcohols in chapter 17. So chapter 17 starts with preparation, then it goes to the reactions of alcohols, including Grignard reaction. One of the very interesting reactions in chapter 17 is Grignard. How does Grignard reaction work? So if you have Rx and you treat it with magnesium in presence of ether in dry conditions, you will generate RMGX. Now RMGX is called Grignard reagent. Grignard reagent can react with ketone RMGX first, and this will work this way. So R is negative. It's going to attack the carbon of the carbonyl, and this will open up. It will generate O minus connected to MgX, and here we have now urine UR, and treatment with H3O plus will result in formation of tertiary alcohol. So this means you form now the tertiary alcohol from ketone. What if you have aldehyde? If you have aldehyde, C double bond OH, you treat it with a Grignard. First RMGX followed by H3O plus. You will form OH, hydrogen, and R, secondary alcohol. This is tertiary alcohol. So tertiary alcohol comes from ketone. Secondary alcohol comes from aldehyde. Formaldehyde will give you, of course, will give you the primary alcohol. One more reaction, which is the ester, C double bond O, OCH3. If you treat it with a Grignard, RMGX followed by H3O plus, then you have R minus that's going to attack the carbon, and this will open up. Now when it comes back, it will kick out the OCH3. So you will first generate ketone, but of course that ketone, which is C double bond O, this is the one that will be formed now. Okay, now this R group, this is ketone, it will not tolerate the presence of Grignard. It will go for another round, and that will result in formation of RROH. This is tertiary alcohol. Okay, so this is why you need here to use two equivalent instead of one equivalent, because if you do one equivalent, it's not going to work. You will get just a mixture of everything. Okay, so this is an intermediate that's encountered here. This is again tertiary carbocation. Okay, can we do this reaction with carboxylic acid? RMGX. Second, H3O plus. Can we do it with the Grignard يا شباب? Can we do this with carboxylic acid?
No.
We cannot, because this one has active hydrogen that will destroy Grignard. So here you will not have a reaction. You will end up having this RH, yani alkyl halide. This R minus will just pick this proton, and the reaction will be terminated. Okay, so again, chapter 17, there are some reactions in oxidation, reduction. I am assuming that you should go over these reactions and know which one will do the oxidation towards completion and which one will stop at the aldehyde level. I will not list them here, but I'll tell you that this is primary alcohol, that when you oxidize it, it will go to aldehyde, C double bond O, H, and this will continue to form RC double bond O, O, H. So aldehyde is very sensitive, very delicate. You cannot just, isolate aldehyde simply. Most of the time it will be oxidized and form the corresponding carboxylic acid. When you oxidize RROH, you will form R, C double bond O, R. Now let me draw this one, like this. So this is R, and this is OH. When you oxidize it, you have no problem. You can use Jones, you can use sodium dichromate, you can use Dismartin, okay? Anyone will work. it's very sensitive here which one you use to stop at the aldehyde level. If you want to stop at the aldehyde level, then you have to use this Martin periodine. This Martin periodine. Otherwise, if you use a stronger oxidizing agent, it will take the primary alcohol to the corresponding carboxylic acid. So these are the main reactions in chapter 7. Okay, so now if you go back here again يا شباب, this sequence that I just talked about is very, very important that you study chapter 8 followed by chapter 11, because 8 together with 11 will help you to understand 17 and 18. Otherwise you will find difficulties in chapter 17 and 18. يعني review chapter 8 for 1 or 2 hours, then since you are at chapter 8, review chapter 9 immediately, because chapter 9 is related to chapter 8. Okay, but of course chapter 9 is not crucial to understand the chapters that are coming later. Now in order to understand 17, you need a combination of 8 and 11 to understand 17 properly. And then if you have 8, 11 and 17, you can move smoothly to chapter 18. It might take you only 1 or 2 hours. You will not struggle. But if you go directly to 17 and 18 and you already forgot chapter 8, you will be in trouble. Okay? طيب. Let me hear from you if you want. يعني maybe we have a few minutes. If you want me to talk about something that is not clear for you. ها يا شباب.
دكتور.
يس.
في الأروماتيسيتي لما يكون عندي 2 رينجز.
اوكي.
كيف أعرف إذا هو أروماتيك ولا لا؟
لما يكون عندك 2 رينجز، هل ال 2 رينجز كونكتد ولا سيبريتد؟ إذا سيبريتد فخلاص كل رينج منهم تعاملها لحال.
كونكتد.
يعني لما يكون عندك على سبيل المثال بنزين رينج وعندك هنا بنزين رينج، خلاص انت هذه تفصلهم عن بعض، تقول انه في عندك 2 aromatic systems isolated. لكن لما يكون في عندك الآن example زي هذا، عندك الآن دبل بوند دبل بوند دبل بوند دبل بوند، لا هذه السيستم interconnected والresonance forms that you draw in one will affect the other one. في الحالة هذه we can consider both of them as one system. فلازم يكون في هذا السيستم عندك شوف 2 4 6 8 10، هنا عندك 10 إلكترونات، فهذا بنسميه aromatic لأنه في 10 إلكترون not because it has 6، لأنه هنا عندك 2 forms are connected. هنا you have 6 electrons 6 electrons. تمام؟ في الحالة هذه بنقول إنه عندنا 2 aromatic rings. هنا we don't have 2 aromatic rings, we have 2 rings that can be classified as aromatic system.
دكتور.
تمام؟
دكتور.
Yeah. So هذه الرينج اللي هنا بنعاملها وكأنها one ring. لكن هذه الرينجز اللي فوق we treat them separately because they are not connected. يعني their resonance forms will not interfere with each other. بس أهم شيء هنا إنك تعرف السيستم إنه لما يكون aromatic إيش الفرق بينه وبين الأنتاي، إيش الفرق بينه وبين اللي هو النون aromatic. طبعا يعني هذا الديفينيشن الآن is يعني changing with time. Now they are doing another definition which is called NICS, but still it's not يعني adopted at the undergraduate level. So the system that is reaching to يعني the system it prefers to be aromatic. Number one, if it's not aromatic it prefers to go as non-aromatic, not anti. Anti is the worst. يعني if we look at this if we look at this example and look at this example, benzene ring is extremely stable. This is extremely unstable. The compound prefers to be anything else but this system. Then anti-aromatic is extremely unstable. يعني هذا compound, it will react with itself because it doesn't like to stay in a form where it's conjugated, planar, and doesn't have the 4n+2. It has 4n electrons. 4n electrons is not a stable system. أيوة يا شباب.
دكتور.
Yeah.
Sometimes in aromaticity we find oxygen. How can we deal with the oxygen?
The same way you deal with nitrogen. You can use the lone pair to consider the system as aromatic. يعني لو كان في عندك الآن هذا السيستم وعندك هنا oxygen وعندك هنا lone pairs. You don't have to consider that oxygen here is contributing 4 electrons. No, oxygen is contributing 2. There's no atom that can contribute more than 2 electrons. The atom will either contribute 1 electron or 2. ما في atom can contribute 4 electrons. عندك اللون pair اللي على الأكسجين, if one of them is incorporated with the aromatic system, it will be p orbital. The other one now will be sp2 or whatever. It will be most likely sp2. But the two lone pairs here cannot be in the same direction, and they have to be perpendicular in each other. Okay, they have to be like an angle of 109 or probably perpendicular. So the two lone pairs, one of them will be included to make this system aromatic, and the other one will be outside the aromatic system. So oxygen, the only difference from nitrogen, that nitrogen has only one lone pair. Either you include it in the aromatic system or you exclude it. Oxygen, you have the chance to include one, but of course, if you don't need this oxygen, then you do not include it in the system if you have something that's already aromatic. Okay? But most of the time you will be including the oxygen to finish this, because this material that is given to you in chapter 15, it explains very well this issue of what is the hybridization, or which orbitals the lone pair of the nitrogen or the lone pair of oxygen is occupying. So it's excellent for you, and it will enable you to understand this topic properly. It's much better than what's explained in the book regarding this issue. So oxygen, nitrogen, sulfur, all you treat them the same. If you need the lone pair, you can use it. Other questions? طيب, how many of you يا شباب already finished the material studying? Let's see hands. Good. يعني the rest did not finish, but if you didn't study again chapters يعني 17, you need to know that you can study chapter 15 and 16. They are not dependent on the previous material that much. But chapter 17 and 18, before you find it very complicated, I would go tonight and study chapter 8, review chapter 11, assuming that you already studied chapter 11, and then move from chapter 11 towards chapter 17 and 18. Again, 17 and 18, they assume that you know 8, you know 11. يعني ترى 8 و 11 أهم 2 chapters أنت تعلمتهم في الأورجانيك chemistry. Of course besides the structure and other aspects اللي تعلمناها في previous chapters. بس regarding reactions and how to deal with reactions, mechanism, synthesis, chapter 8, chapter 11 are the key components. That everything else after that depends on them. Even if you are taking organic 2, if you are weak in these 2 chapters, you will struggle in organic 2. If you are okay, things are moving smooth for you, then you have no problem in any organic course that you will take later on, or organic topic. Okay شباب, if no questions يعني خلاص, and I wish that this session was helpful, and I wish you all the best inshallah in the exam after tomorrow.